Hi folks, and welcome back to our live session reviews. And tonight we're going to be talking about optimization in definite integrals, along with the definition of the definite integral and how to solve integrals of that type. So if you have any questions along the way, there's that chat box over there, so please just type in the chat and I'll be happy to answer them as they come about. So without further ado, we're going to get started, and we'll start with a Norman window problem. So this is pretty famous in terms of it's a one you see oftentimes in calculus. So what's a Norman window? A Norman window has the shape of a rectangle. So we have some form of a rectangle right here, surrounded by a circle. So you have some little circle or semicircle up top. Okay, and we have to suppose that the outer perimeter is 600 centimeters, so meaning this distance right around all the way on the outside. Determine the exact value of the diameter of the circle that maximizes the area. So the diameter, what we'll call is x for right now. Now, we have some missing pieces that we might want. Well, notice that if the diameter is x, that means the bottom of this rectangle also is x. And then we can have the other side be L for right now. You can pick whatever letter you want, but at the end of the day, we have a nice little formula to kind of work with to give us some values here. So the perimeter, first off, we know that that equals 600 centimeters, but the perimeter would also be given in another format. We can write it as, well, notice you can travel along, and so what that is, that's distance traveled along here. So we could travel along this distance, which gives us L. Then we travel along this distance, which is another x, or not another x, but an x, and then we have this distance right here, which is L again. And then finally, what's our last distance? Well, we got to figure out this distance of the semicircle, right? And so what gives us the distance of a semicircle traveled around? Well, notice the circumference of a circle would usually do the trick for us. But we have half the circumference, so it's half 2 pi what's usually r. Well, so half, because it's a semicircle, then we have 2 pi, and it's our radius. But notice our radius of this circle would be 1/2 x, or x over 2. So 1/2 x. And so this gives us a nice formula for our perimeter. We get 2L, and then what will happen? Well, we can factor out an x of the other term. So we have x times this big old quantity. Let's see what happens. Well, we have 1x here, and so the 1/2 and 2 will cancel, and you're left with 1/2 pi, or pi over 2x. So the other portion we can write as 1 plus pi over 2 times x. Okay, so we can have our perimeter equation, and notice the perimeter, we can plug in the 600 equals 2L plus 1 plus pi over 2 times x. And so from here, let's think of what we want to do here. We want to determine the exact value, so we want an exact value, no approximations with decimals or anything like that, of the diameter. So we're looking for, this is what we labeled to be x. Okay, you could have labeled it d or whatever the case may be, it works out all the same. That maximizes the area of the window. So think about another way you could ask this problem is that allows the most amount of light to get through. Okay, so if we have that in mind, maximizing this area, we have to find an area equation. Well, the area equation you can think of as, since we have things involved here, we can work with, this is the area of the rectangle plus the area of the semicircle. Right? And so the area of the rectangle, that's not too bad. This is x times L. Okay, so that turned out to be all right. And then the area of the semicircle, remember the area of a circle is 1/2, or not 1/2, but pi r squared. But so we have half of that, so 1/2 pi r squared. And remember our r value is 1/2 x. So this is 1/2 pi times 1/2 x, the quantity squared. Okay, so we're in good shape. If the only thing, if we were to try and, the idea with all these is to take a derivative set it equal to 0, but we have that stinking L sitting right there. So that's going to be hard, a little bit harder for us to work with. And so we usually want to get these optimization problems down to one variable, and that's what we'll do with this scenario right here. So you have 600 equals 2L plus this 1 plus pi over 2x. Well, we can move that x over to the other side, so you get 600 minus 1 plus pi over 2x equals 2L. And so now just take both sides and divide by 2, and so you can write that as 1/2 600 minus 1 plus pi over 2 x equals L. Okay, so that means our area equation. I should have made some comments here actually early on. Little FYI, x, let's think about how far x can go. Well, x couldn't be 0 because then you have a straight line, right? So notice x falls, it has to be greater than 0, and then what's the maximum x could be? Well, notice if you're 600, you're a flat line in the other regards because the whole diameter is there. So your x has to range between 0 and 600. That's a little side note that we're going to have to consider a little bit later on. So now moving forward from here, what is our area equal? Well, we can write this as x times, well, this will look nasty, but we can simplify this a little bit in just a second. So you get 1/2 600 minus 1 plus pi over 2 times x, and then we'll close that off. And then do we close off that other parenthesis? Yeah, there we go. Plus our next one, we can write as pi over 2 times 1/4 x squared. Okay, so what does this equal? Well, you can distribute this x. Notice the 1/2 gets distributed, right? So when you distribute that 1/2, you'll get 300. And so that when you multiply that x on through, you get 300x. Okay. And now the other interesting part, we'll have minus 1/2 and then minus pi over 4. And each of those are x squared. So minus, because the x has to also go on over this way. So it goes to this first part and it goes over there. So you get minus, we'll have 1/2 x squared minus pi over 4x squared, and then plus pi over 8 x squared. Well, that's going to be convenient because pi over 4, that's negative 2 pi over 8 right there. So we can combine this, and so this whole thing becomes 300x, which isn't so bad, minus, and then we'll factor this out here real quick. We'll factor out the 1/2 from that first x squared term, and then we'll factor out, it'll become negative pi over 4, so that becomes, we'll write plus because we have that negative sitting out front, or the negative pi over 4 becomes negative 2 pi over 8, plus pi over 8 would be minus pi over 8, so that becomes plus pi over 8 times x squared. Okay, so this area function, we'll start to call this now a of x equals 300x minus that 1/2 plus pi over 8 x squared. So that means what we want to do is take the derivative and set it equal to 0. So a prime of x equals, what do we get? Well, we'll get 300 minus, all this is a constant, so that isn't going to make much of a difference, 1/2 plus pi over 8 times 2x. Okay, well that looks good, and so now we set this equal to 0, so 0 equals 300 minus our 1/2 plus pi over 8 times x. And notice we really don't have anything, oh I'm sorry, not 1/2 pi over 8. If I distribute that 2 on through, notice we'll get 1 plus pi over 4 now times x. We can move that over to the other side and try and solve this thing. So we'll get, and I'll just leave the 300 on the left hand side because moving the other to the right hand side. So moving this 1 plus pi over 4 to the left hand side, it doesn't matter which side I have the equal sign as long as I'm having things appear accordingly. So you get 1 plus pi over 4 times x. And so divide both sides by that 1 plus pi over 4, so you get 300 over 1 plus pi over 4 equals x. Now, this doesn't tell us if it's a minimum or a maximum, so what we'll have to do now is actually draw that number line. And now remember, we have 0 and 600 are two values that are endpoints for this, and somewhere in between here is 300 over 1 plus pi over 4. Okay, all of those are x values, and what we want to do is find a prime of x. Now this might be hard to approximate as is, right? So how do we actually go about solving this thing? Well, the real trick is thinking about what is pi over 4, right? So when it comes down to it, pi over 4, that's 3/4 essentially if you really wanted to round it. So this number is something less than 2. So this number is less than 150, or not less than 150. So it's going to be greater than 150 because you have 300 over 2 would be somewhat larger than 300 over 1 plus pi over 4, right? No, I'm sorry, I put that backwards. Is less than that. So what that means is, what we can say in this case, then this is equal to 150. And so we have x is greater than 150 at the very least, right? On the other hand, you can't say, well, so you can pick a number, it's greater than 150. 1, for example, if you plug in the number 1, what's going to happen? Well, if you plug in a number 1, notice you would never get 300 down below. So this is also less than, so while it might be greater than the 150, it's not as far down as, say, hold on one second. So 300 divided by that would be 2. Yeah, that must be larger. So yeah, that's greater than 150. And on the other hand, it's not all the way up to 300, for example, because you've got a little bit more wiggle room. So this thing has to be less than, say, 300. So you can pick numbers in any range and kind of compare. I'd go less than 150, I'd go greater than 300, and those could be things that you can plug in. So any value that you can plug in between there, I'll take 1 just to make our life easy. You plug it into the original equation, or original derivative, and you get 300 minus 1 plus pi over 4. Notice that's 300 minus something that's close to 2. Well, that's going to be a positive number. That's all that we care about. So this thing's positive, and this is 0 for the derivative. And now we'll take a number that's really close to 600, right? 500 would work, right? Well, if you do 500, notice this is going to be 300 minus, well, 500 times some number larger than 1, so that's going to be greater than 500. So 300 minus 500 even is negative. So this whole thing is negative, right? So what does this tell us? Well, it tells us we go from increasing to decreasing right there. Okay? So if we go from increasing to decreasing, what does that tell us? It tells us that this is a maximum. Right? And we don't have endpoints because 0 and 600 can't happen. So that means this is our maximum on this interval. So that's our final answer, 300 over 1 plus pi over 4. If you wanted to brush that up, you can multiply both the numerator and denominator by 4. And so you could also put, let's see if I can squeeze that in here, x equals 1200 over 4 plus pi would do the trick as well. Okay, if there's any questions, please let me know. I don't see any as of this point, so I'll keep on trucking along with another optimization problem. So our next one that we're going to take a look at is this one with electric current. So if you have an electric current passing through two resistors with resistance R and S, we'll say, little r and little s, and let's assume they're connected in parallel. The combined resistance, where we'll use a capital R, can be calculated from this equation. The 1 over capital R equals 1 over little r plus 1 over s. Okay? So where this capital R, lowercase r, and s are all positive values, so we aren't dealing with anything negative there. So if s is a constant, so assume we have everything constant there, we want to determine if the capital R is an increasing or decreasing function in terms of little r, or it might be doing some waving back and forth. Let's see. Well, we have a nice equation here, and s is a constant. We could go for the gusto right away and try and solve for things in terms of we'd have a big R involved and all that stuff. What I would recommend though is, in this case, I would actually solve for the big R in terms of the other values. So how the heck do we do that? Well, so first things first, we could flip this over. So we could say capital R equals, and if I flip that over, I have to flip over the other side. So we go 1 over R, or 1 over little r, and plus 1 over s, right? So you flip those over and we get this. But this doesn't look nice in terms of taking a derivative. So what happens? So this is just the original equation that we're working with. You get R equals, let's do this, 1 over R plus 1 over S. Remember, we need a common denominator to kind of work with that, so we'll multiply by RS in both the numerator and denominator. And so this thing equals RS over, this would become S plus R. Now remember, little r is your variable, S is a constant. So we can actually take this derivative, sorry, with respect to the little r, not s, s is our constant. And when we take that derivative, what do we get? Well, you look and we have to use a quotient rule. So we get s plus r, the quantity squared. And then what happens? Well, when we take the derivative of the top, right, remember lowercase r is our variable, so that means s would be with what's left over, and we have to multiply that by the denominator, which is s plus r. Then we leave the numerator alone, and we take the derivative of the denominator, which is just 1. Okay? So what does this become? Well, notice when we distribute this s to both parts, what happens? Well, we get RS here, so this term will cancel off with that term, and you're left with just s squared, oops, over S plus R, the quantity squared. Questions on that piece? So if this is the case, and we have, this is our final sort of answer, let's think about what happens. Well, if you're trying to determine when this thing equals 0, it can't, right? So even if you started at, say, R being, it has to be positive, so we have 0 sitting here, and we can't equal that. Remember, R must be greater than 0, since this thing's positive for our R's and S's and capital R's and stuff. Okay? So, what happens? Well, as this thing is our equation, this dr over, or d capital R over d little r takes place, what we're actually looking at, well, this thing, we can plug in any value, no matter what it is, we're going to get a positive number every single time. So what does that mean is happening to our function? Like what's going on with our original function then? Well, if that's the case, then what must be happening is we're increasing for all values, no matter what. We always have increasing going on. And so if that's the case, we have increasing, that tells us the function must be an increasing function. So R of little r, I should say, is an increasing function. For all r greater than 0, right? And that's our whole interval, because that's all we basically have for values. We just said, hey, it's positive of some sort. Okay, any questions on that one? All right, I don't see any more questions. Hopefully everything was answered along the way there. Kind of saw something pop up there real quick, so try to answer it as we kept on going. All right, so the next optimization problem. Let's let A and B be positive numbers. And we want to find the length of the shortest line segment that is cut off by the first quadrant and passes through the point AB. What the heck is going on here? So what I'd recommend is drawing a graph. And I don't know where the heck it is, but somewhere, it might not be symmetrical, maybe way off in the distance, but we'll just say we have a point AB. Now let's think about, if we want a line segment that is cut off by the first quadrant, if we don't have a negative sloping line, all of a sudden what's going to happen is we have something where the line goes on forever and ever. So we want our slope of our line to be negative. That's hopefully pretty obvious right here. So I'll draw the line that kind of goes through there, and let's use black. And so I don't know what this line's going to look like necessarily. I mean, it could be really steep, it could be really shallow, but something like this, okay? So we have a line. Now, the real question to this is what in the heck's the equation for the line? All we're given is this point AB. What the heck? Right? So, at the end of the day, we can find an equation for that line in terms of the points. And it goes y minus, our y1 value is b, equals, we don't know what the heck m is, and then we'll have x minus our x1 value, so our point on our line is a. So this came from the point slope formula. Or point slope equation of a line. So now that we have that, we're in pretty good shape. Let's see what we can do from here. So we want to try and minimize a distance, or find the length of the shortest line. So now we have 2 points right here and right here. Let's call this, we know this is a y-intercept, so let's call this 0 y sub 1 now, and let's call this x1 comma 0, or you can call it your x-intercept and your y-intercept, but we know there's something going on there. And then we have a distance between those 2 points. What's the distance? How do we calculate that? Well, let's say you didn't know the distance formula. Notice this is a triangle, right? That's the beauty of the distance formula. It just stems from a triangle. This distance is y1. This distance is x1. So if you look, what should our formula be? Well, you have the distance squared, right? Because that's our length of our hypotenuse. So the distance squared would equal x1 squared plus y1 squared, right? But we don't have distance squared. We have, this is a square root going on right there. Now the problem with that is we don't know what the heck x1 is. We don't know what the heck y1 is. And we have just an a and a b, and that's pretty much all we're really working with here, right? So how do we go about this? Well, we do have this equation. And what we can do is we can use this. And what do I mean by that? Well, if x1, 0 is a point on the curve, that means when we plug in 0 for y, we can get negative b equals m, and then instead of x, we'll have x1 minus a, right? And so that means if we actually solve for m, or we can solve for rather than solve for m, let's solve for actually x1, and we could put x1 in terms of this m. So we have negative b over m equals x1 minus a, and so that means that x1 equals a minus b over m. In a similar manner, we'll use our other point and plug that in. Now we have y1 minus b equals m, and then it goes 0 minus a, right? And if we're to solve for that, what do we get? We get y1, this one will be a little bit easier, equals negative a times m plus b. Or we could rewrite that as b minus a times m. Okay, whoopity freaking do, right? So when you look at this, what do we do with all this junk? Well, we have that distance. Remember, a and b, just a little side note here, these things are constants, right? So this looks scary, but basically we have our variable and it's m. So we have distance equals the square root of, well, x1 squared will be a minus b over m, the quantity squared, plus y1 squared is b minus am, the quantity squared. So what the heck does this thing equal? Well, this equals the square root, well, actually, just to make life easy, we do have m in 2 parts, right? Let's make our life easy. We'll leave it this way. But what it does is this gives us a formula: d of m equals the square root of a minus b over m, the quantity squared, plus b minus am, the quantity squared. And now we can start to take our derivative because we have our one variable, it's m. So d prime of m, notice the square root, it looks scary, but this is 1 over 2 times the square root of a minus b over m, the quantity squared, plus b minus am, the quantity squared. But regardless of what happens, that's always some basically positive number, unless m equals 0, but we can't have the slope be 0, because that would be an infinite line anyway. So we don't have to worry about cases like that. Remember, we wanted, in our discussions, we wanted the slope of this thing to be less than 0. So from negative infinity to 0, we don't want to include 0 either. So we're in good shape in terms of all that. But now we need to use the chain rule. So times, we get 2 times this a minus b over m, plus, and then it'll be 2 times b minus am. So notice, in order for this thing to equal 0, it's nothing to do with the denominator. In fact, we can kind of shuttle a lot of that stuff all around. The 2's will cancel, and so like this 2 and this 2 would cancel off of that 2. So what are we left with? We're left with 0 equals a minus b over m plus b minus am. Right? Questions on that? All right. So moving forward from here, we have a couple different ways to approach this thing. Now, let's see. What's kind of our best approach? So if you look at, we can combine this first term to make it look a little bit nicer. So if we have 0 equals, we could write this as am minus b over m, right, plus b minus am. Right? And moving forward from there, we can try and solve this a slightly different way. If we go move the top and bottom by -1, so we get, what do we have? We have if we move top and bottom by -1, notice you'll get b minus am plus our b minus am. So this means that, all this equals 0, my apologies there. So you can factor out a b minus am. And so, I'm sorry, I made a slight error here. Oops, I made a big error there. In taking my derivative, I got a little sloppy. And let's fix that real quick. I can use the same type of idea, but notice when I had that 2 times a minus b over m, I forgot to multiply by the derivative of this m in the denominator. So that'd be times, usually I could factor out the negative 1b, but then it becomes negative 1 over m squared, so that would be b over m squared. So let me actually rewrite that. My apologies there. Got a little ahead of myself. So taking a look at this, you have the 2 times a minus b over m. All that should be multiplied, well, not all of it actually. Well, yeah, times the derivative of the inside, so that would be times negative, and then it becomes negative 1 over m squared times b. So the negative and negative makes it positive, so that's b over m squared. Right? But you'll see the setup of this, and then it goes to b minus am, and then I should be careful here. I should also have a negative a appearing right there. And what we have is 0 equals, and that 2 would cancel there. So 0 equals, I'll rewrite this and kind of do a Texas two-step here. So I get am minus b over m times b over m squared, plus, and then we have b minus am times negative a. Okay, and so we can rewrite this, this am minus b, you could write this as b minus am, but then we'd have to multiply it by negative 1 is another way to write it. And so that's going to be useful in terms of how we can rewrite this thing in a second here. I'll rewrite it over on this part. So we can write this as b minus am times, now we can move that other m in the denominator with the negative 1 in the b, so you get negative b over m cubed. So notice all we're doing actually right now is just algebra. And then the other part, we have b minus am times negative a. Moving that forward, we can factor out a b minus a over b minus am, and we get the rest is just negative b over m cubed, and then it goes minus a. Okay, so now I think we're ready to rock and roll with this thing. So notice you have two factors. You're solving for m. In the first case, it's pretty straightforward. You get m equals b over a. But this is greater than 0. And since it's greater than 0, because a, b were in the first quadrant, that's why we know it's greater than 0. So not a possible solution. Okay, so the other case is 0 equals negative b over m cubed minus a. And so another way to write that, move the a on over, and so you get a m cubed equals negative b. And so m cubed equals negative b over a, and this means that m equals negative the cube root of b over a. Wowzers. So now what we have to think about is, and I'll try and fit this in somewhere, we have this cutoff point where you have 0. You have the negative cube root of b over a, and these are your m values. You know that d prime of m equals 0 at that point. And so how can we plug in other values to try and work it? Well, if you plugged in, say, m equals 1/2 times that negative cube root of b over a, you know that that would be closer to the 0 than anything else. And then if you did 2 times that negative cube root of b over a, you'd be on the other side of the fence. So at the end of the day, when we cube that, notice the b's cancel right away and it just puts the a up there. If we have a 1/2 and we're cubing that, you get this negative negative makes a positive, so you'd have 1/8 in the case where we use 1/2. So 1/8 a minus a, well, that'd be negative 7/8 a. So that means this side is a negative, and if we plugged in a 2, oh, I'm sorry, I said it would make a positive. So notice that make a 1/8 in the denominator, so that comes up to the numerator, so that makes it positive 1/8. So, or positive 8 in that case. So in the other case, when I put the 2 down below, that's the one I was originally talking about. So the 2 stays down in the denominator. When I cube it, I get the 8, and there's the 1/8, and so I was putting that on the wrong side. So the 1/2, or when I use something like 1/2 times negative cube root of b over a, that would result in a positive, versus using something like 2 times the negative cube root of b over a. That would result in something negative. Okay, so that means we are decreasing to increasing. That means that this is our minimum. And since we have no endpoints to check, because they aren't included in an interval, we know that that is the minimum. Hopefully that makes sense in terms of what's going on this one. And you can see where some values aren't possible solutions because it comes back to the domain. That's why I really like this problem, to see something like that. So now moving forward from here, we're going to evaluate some integrals. Pretend this is like straight lines, and then we have a semicircle going on here. And so unless otherwise noted, I'm not trying to pull some tricks. You do see a semicircle, you do see a line. Don't let your eyes fool you. So in the first case, the integral from 0 to 2 of g of x, what are we looking at? Well, you cut off as 2, and you have a starting point of 0, and you're looking at the curve, and you look at the area between the x-axis and the curve. So you're basically shading in this area right here. So what's the area of that shape? So this should equal the area of that triangle. Well, that's 1/2 our base, and so I'll write 1/2 BH just for now. So 1/2 our base. Well, what's our base? Is 2. And what's our height? Well, that's 4. And so notice that thing equals 4, and you're done. Okay, so what about 2 to 6? So now we'll work this one in purple, I'd say. So here's 2, and we go to, this is 3, 4, 5, 6. So you have something like that. Now down below there is something that happens when you see something below the x-axis. That's a negative value. So this is negative the area of the semicircle. Okay, so from 2 to 6, well, what happens? Well, we get negative, and then it goes 1/2 pi r squared. What's our radius? Well, our radius of our semicircle, notice that would be our radius right there, and that distance is 2. So this thing equals negative 1/2 pi times 2 squared, which is 4. 4 divided by 2 gives us 2, so you get negative 2 pi. Okay, so for our third one, we're going to use some properties of integrals, and it's going to come in handy. We'll start with the fact that we know an integral from 0 to 2. So you can write this as an integral from 0 to 2 of g of x dx. And then we can continue on, and we can write an integral from 2 to 6 of g of x dx. And then last but certainly not least, we can add on an integral from 6 to 7 of g of x dx. That's the beauty of these integrals. You can break them up into wherever you see fit. That makes your calculations easier. Okay. So with that in mind, we have, well, the first case was 4. So that part is pretty much done for. And then the next part, plus we have a negative 2 pi. And the last part, notice this is a triangle. And our base and height are both 1. So you have 1/2, 1 times 1. Okay, and that's positive because it's above the x-axis. So that's 4 is 8 over 2. So you can write this as 9 over 2 minus 2 pi. and you're done. So you have each of those answers sitting right there for you. Okay, in a similar manner, so you saw how we break them up with addition, you can also do some maneuvers with multiplication. And in our case here, you have, this might look tough because we have 2 times f of x from 0 to 2. Well, all you need to do is take 2 times the integral from 0 to 2 of f of x dx. Now what is that? Well, that means we go from 0 to 2, we shade in this area, that's what we're trying to find. So that means it's 2 times negative the area of the semicircle. Okay, well, that means this is 2 times negative 1/2 pi times, what's our radius? Well, in this case, our radius of our semicircle would be this distance here, which is 1. Okay, well, 2 times negative 1/2 is negative 1 times pi, and then we have this whole thing would just be negative pi, and we're done. Okay, in a similar manner, we can work with this next one. We can pull out the 3 from 0 to 6 of f of x dx. And that might be hard because we have 2 separate circles, right, that we want to deal with. So this equals 3 times, and we'll put the quantity here. We go from 0 to 2 of f of x dx. That's a nice one for us. Plus another integral from 2 to 6 of f of x dx. And we can solve this thing. Notice both of those are semicircles, so hopefully we're pretty familiar with the formula. This is 3 times. We know the first one from up above. That's negative pi. Plus our second one, well, it goes 1/2 pi. What's our radius? Well, notice our radius, we have a radius once again of 2 is our magical value. So pi times 2 squared. Oh, I'm sorry, in the last one I didn't put the 1 squared, but hopefully you can see 1 squared is 1, just an FYI. So in this case, that's we'll get 3 times negative pi plus 2 pi. So notice that just 2 pi minus pi makes pi. So this whole thing equals 3 pi. Okay, so we're rocking and rolling now. A little more interesting on this next one, from 1 to 4. Well, we can kind of, there's a couple different ways to work this one. We could break it up from 1 to 2 and then 2 to 4. So one route would be from 1 to 2, and we'll pull out the 4 out in front of all this. 1 to 2 of f of x dx. Plus 2 to 4 of f of x dx. Another route you could actually do, though, is actually go from 0 to 6 like we had before. Granted, it's not 4 anymore, right? So we have to adjust that number. But you can go from 0 to 6, and then subtract off from 4 to 6, and subtract off from 0 to 1. If you subtract off those integrals, you'll get the same answer. But so at the end of the day, what are we dealing with? We're dealing with a quarter of a circle now. So 1/4, and then it's negative. So this is, well, let me put negative 1/4 first. Negative 1/4 pi times 1 squared. And then plus another 1/4, and then it goes pi times 2 squared. All right, you have 2 quarter circles. And so what does this make? Well, this is 4. 4's will cancel. You're left with pi. And then minus 1/4. So this is equal to 4 times 3/4 pi, which equals 3 pi. Okay, last but not least, this is the fun one. So what the heck happens with this absolute value? Well, the absolute value basically, whoops. So here's the absolute value graph, drawn in pink. So everything you see in pink is the absolute value. What did we just do? Well, we turned everything that was negative to positive, and then we drew the graph. So really what this thing becomes is the 3 can just come out in front. That's not going to make a difference. But we go our integral from 1 to 2 of the absolute value of f of x dx, which we now should be able to calculate, plus the integral from 2 to 6 of f of x dx. The reason why we could just get rid of the absolute value in that case is because that is the same exact graph, right? You can't always do that. Just be careful. We can only do it for that case. We actually already have what. Oh, we don't have from the 2 to 6 exactly. Well, we kind of do, but we'll go through the calculation. It doesn't hurt us to do it one more time. So in this case, we get 3, and then this will be 1/4, and then it goes pi, and now it's positive, notice, pi times 1 squared, plus, in our other case, we'll get 1/2, because it's a semicircle, and then we have pi times 2 squared. Okay, so this is going to be 3 times, we'll have 1/4 pi plus, that'll be 2 pi, right? So 2 pi plus 1/4 pi, that would make, what, 9/4 pi? So we have 27 over 4 pi, and that's our final answer. Okay, that one can trip up a lot of people, but as I said, if you draw the graph, it becomes a little bit more obvious in this case. So last but certainly not least, we'll leave this off with is using Riemann sums to evaluate the integral. So in order to do that, you need a nice Riemann sum formula. So that goes the limit as n goes to infinity of the summation, and then I equals 1 to n, and it goes b minus a over n. That's the width of every rectangle. Okay, and then it's f of a plus, so a being the bottom bound, and I times b minus a over n. So essentially you have a width of a rectangle and then the height of the rectangle right here for all of your rectangles. And if you're starting at I equals 1 and you're finishing at n, you're using a right endpoint approximation. If you start at I equals 0 and finish at n minus 1, you're using a left endpoint approximation. So this thing equals the integral from a to b of f of x dx. So in our case, what do we have? Well, we have a equals 1, we have b equals 3. Okay, so that means b minus a over n would equal 3 minus 1 over n, which is 2 over n. Okay, and now we have f of x equals 4x minus 3x squared. And so f of a plus I times b minus a over n is f of, well, a is 1, our I is just I, and then our b minus a over n we just said is 2 over n. So now we got to plug those in. This whole thing goes in for the x values, so this thing equals 4 times 1 plus I over 2n. And then we go minus 3 times 1 plus I times 2 over n, the 20 squared. Well, that might take a little bit of work, but we can work with this. So we have 4 plus, and I'll rewrite this as 8 over n times I, minus 3 times, when you complete a square, just a little side note, you have a plus b, the 20 squared, equals a squared plus 2ab plus b squared. So this is 1 plus 4 over ni, because we have the 2 times 1 is 2, times another 2 over n, so that makes 4 over n, and then times that I just wrote it in a different place. And then you got to square that last term, so that'll be I squared, and then you'll have a 4 over n squared. And so just writing it in a slightly different order, you get something like that. So what does this make? Well, notice we have a 4, and then we'll have this minus 3 goes times each of these. Okay? So 4 minus 3 first is 1. Notice the I terms. You have 8 over n and then minus 12 over n. So that would make minus 4 over ni. And then 3 times that negative 3 times that last piece would be negative 12 over n squared I squared. So I think we're ready to rock and roll with this thing. So the integral from 1 to 3 of our 4x minus 3x squared dx equals the limit as n goes to infinity of the summation I equals 1 to n, and now b minus a over n. Well, that's going to be 2 over n. And then f of a plus I times b minus a over n. We found that. That's 1 minus 4 over n I minus 12 over n squared I squared. Okay, so this thing equals the limit as n goes to infinity. And we can write this as 3 different sums where we've distributed the 2 over n to each term. Okay, so the first sum is I equals 1 to n of just 2 over n. Okay, then our next sum, so we'll write minus our second sum. Well, actually I'll put plus our second sum. We'll talk about the minus in just a second. I equals 1 to n of negative 4 over ni, and then plus a summation I equals 1 to n of negative 12 over n squared I squared. Now the beautiful thing here is the only thing that's actually changing is the I value. So if you don't see an I, you can pull everything else out in front. So for example, in that first one, we can pull the 2 over n out in front, and we have a summation I equals 1 to n of just 1. We can pull the minus 4 over n out, and we have a summation I equals 1 to n of just I. And we can pull the 12 over n squared out, and we can take a summation I equals 1 to n of I squared. We're going to change colors here just to kind of finish this thing off. So what's happening? Well, we have some information that we're going to need. First off, the summation I equals 1 to n of 1. What the heck is that? Well, think about it. If n was 3, so I go 1 plus 1 plus 1. Well, it's 3. If I had n be 5, it'd be 1 plus 1 plus 1 plus 1 plus 1, which is 5. So the summation of 1 n times equals n. Oh, let me put parentheses around all this junk. So this thing becomes the limit as n goes to infinity of, well, this would be the first case, 2 over n times n. You have a couple other formulas. This one was proven by Gauss a long time ago. The summation, if I go 1 plus 2 plus 3 plus 4 plus 5 all the way up to n, right? The formula goes n times n plus 1 all over 2. The summation for I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 all over 6. And the summation I equals 1 to n of I cubed, if you ever need that, would be n times m plus 1 all over 2, and then that quantity squared. So this means that we have minus 4 over n Hold on one second. I forgot, backtracking real quick. When I did the 2 over n, I distributed it to the first one. I did not do it to the second two terms. So this is 8 over n squared, and this is 24 over n cubed. So that means this is 8 over n squared, and this is 24 over n cubed. Okay, good thing we were using a different colored pen. So this is 8 over n squared, and then this is times n times m plus 1 all over 2 minus 24 over n cubed times n times m plus 1 times 2m plus 1 all over 6. So first off, let's start noticing n's cancel there. The square will cancel off with that end. This will become a square here because it'll cancel off with that end. So this whole limit business, and if you've done things correct, you should always have limits involved for these pieces. So limit as n goes to infinity, we have 2 minus 8 over 2, by the way, that's going to be 4. Okay, 24 over 6 is also 4. Well, that's convenient. So we have 4 times m plus 1 over n, and then minus another 4, and then another way for us to write this will be m plus 1 over n, and then we'll multiply the 2m plus 1 all over n as well. Okay, so all this equals, well, notice you have this whole thing goes to 1. You can use L'Hopital's rule. This thing, same exact result, that's 1. This one is 2. So you get 2 minus 4 minus 8, so that should equal 10. Now let's see a shortcut here. So this is using Riemann sums. When we try and take this, what we'll actually look at and what you'll see coming up is there's an antiderivative associated with this. And the antiderivative, so meaning, what does that mean? That means we take the derivative of this function and we get 4x. So what gives us 4x when we take the derivative? 2x squared. Right? All I did is I added 1 to the exponent. So this is x to the first, so I made it x squared. And then I divided by that number. So 4 divided by that x1 plus 1. So 4 divided by 1 plus 1 is just going to be 2 overall. And then same thing, I add 1 and then I divide by that number, that's our new exponent. So this thing actually becomes x cubed. And so if I plug in, so let's say I have 2x squared minus x cubed, and I'm going to write this a fancy way, so it looks kind of fancy, but all that means is I'm going to plug in 3 into both the x values. And so we get 3 squared minus 3 cubed minus, in our next case, we'll get 2 times 1 squared minus 1 cubed. So what does this give us? Well, so that's 9. It's times 2 makes 18 minus 27. Oh, I'm sorry, I wrote 10. It should have been negative 10 over here. Negative 10 is our final answer. So minus, notice this goes 2 minus 1. So that's negative 9 minus 1. That makes negative 10. Is that a coincidence? By no means. So that's where we're going, and we're heading to these antiderivatives. Actually, will calculate the definite integrals for us in a much quicker time. So that's what we're going to start to do. So hopefully, I don't see any questions left, and hopefully this made sense in terms of what's going on. Sorry for the few hiccups along the way, just missing constants, but that stuff does happen, as you can see. Just make sure you can kind of check your work along the way. You're kind of always going back, double checking, and that's what I did a few times, if you notice. So hope you all have a good one. If you have any other questions, just let me know.